lab, we're going to invent some calculus. Remember all those Riemann sums you've been doing with rectangles? We're actually going to do them and find the center of mass of a semicircle by hand using our basic discrete definition from last year. To make your semicircle, pick your favorite color to share with a partner. Draw a diameter that goes exactly through the marked radius, which you can see based on where the compass is, and cut it out. Once you've got your semicircle, measure the radius. The more pieces you have, the better your data will be. You will want to divide your radius into about 10 equal pieces. So if this is a radius of 7 centimeters, I would make tick marks here every 7 millimeters or so. Once you've drawn out your rectangles in the appropriate places, trace them out. Your job will be to measure the location of each rectangle as well as its mass and record it in the data table. We've measured the center of mass for a system of particles. Now we're going to have a system of rectangles. Does neatness count? Yes, actually, neatness does count. Notice that your calculus methods actually do slice all these shapes into rectangles, not trapezoids, not random nonlinear quadrilaterals. If you are having trouble holding the ruler straight, get a protractor and make sure that your straight lines are really straight. You may have up to 13% error simply based on whether or not you can draw a straight line. Once you have all your rectangles drawn and labeled, measure the location of each one, starting from the bottom and going up. Again, you'll want to lay your ruler flat and make sure you're going absolutely straight and through the center. Once you've measured the center of each rectangle, 0.4 centimeters, 0.7 centimeters, etc., record that information on your data table. Label each rectangle as you go, either with piece number 1, piece number 2, or with the actual height it is. Somebody will sneeze over the course of this lab. You will lose your foam pieces on the floor, and then you will have to stack them all over again. Labeling will make them that much easier. When you're ready, take out a scissors and cut your rectangles. You'll be very glad that you've labeled them. If it looks like the bell is going to ring anytime in the foreseeable future, take some clear Scotch tape and tape all of your pieces together. If you lose one of them in your binder before you finish your poster, you will have to start this lab all over again, and it will drive you nuts. Make sure the tape is touching every piece, especially this little one up here, which is liable to get lost. If you still have plenty of time left in the period, go across the hall to the AP Chem lab and use the AP Chem balance, the good one, with the glass doors that can measure down to the nearest microgram, measure the mass of each of your rectangles, and record it in your data table. Once you have the mass and the location of the center for each of the rectangles, you can use the same formula that we use for center of mass, the weighted average, mass times location, divided by total mass, to locate the center of mass for your rectangle. Now comes the calculus. Instead of taking the sum of each of a number of finite pieces, we'll take the integral that is the sum of each number of infinite pieces. dm is each one of your pieces. You had 10 of them before when you made your cuts with scissors. Now you're going to have an infinite amount. The first thing we have to do, as in every calculus problem, is to solve for dm. This is a two-dimensional problem, so instead of using rho, mass over volume, three-dimensional density, we're going to use sigma, our area mass density, which is defined as the total mass, which you have from your lab, divided by the total area, which shouldn't be so bad for a semicircle if you know the radius. By definition, if the mass density is constant, this is also going to be dm over dA. So, for your first trick, solve for dm using sigma, total mass, total area, and dA, and substitute into your integral up here to get an expression in terms of dA. dA is a piece. in terms of the rectangles that you cut earlier, it's those literal blue or purple or green slices of rectangle that you cut your semicircle into. This is the regular one-variable calculus that most people learn in high school. If you wish, mathematically, to build a semicircle out of rectangles, examine each one of these rectangles. What's the area of each rectangle? For instance, I think you know the difference between this point and this point. I think you know which axis these are, and I think you can probably get an excellent answer for the length from here to here. If this is x, what's this? Area of a rectangle is easy. It's base times height. The height of every single one of these pieces is dy. 2x dy, dA. There's your area. Work it out. Now, unfortunately, we can't integrate with x and a dy. That means we need a formula for x and y that locates this point here. That is, we need a formula for the y of a circle, or in this case a semicircle, in terms of x. And, oh yes, what was that? R. Last time I checked, the formula for a circle looked something like this. So solving that for x should help you get 2x dy and be able to integrate it nicely in terms of y. All right, I lied. It's not like at all. It's u substitution. Get as far as you can. When you get to something that you simply can't integrate, that is your cue to define u. U is anything you wish wasn't there. Set that equal to u. Find du dy. Solve for du. And see what you have to do with this dy over here to get it into a form you can integrate. Alternatively, you can use multidimensional calculus, two-variable calculus, where we have dr going out this way and theta sweeping around from 0 to pi. Both of these methods are shown online. Pick your favorite one. Good luck.